Robert Powell has a BS in chemistry and is a former collegiate debater. He has 28 years experience in engineering management in the semiconductor industry while working at Advanced Micro Devices. He has taken numerous internal courses related to device physics, the design of experiments, and statistical analysis. He helped Advanced Micro Devices, a company, develop its first flash memory technology that is used in today's flash cards for cameras, PCs, video cameras, and other products. His experience includes managing a state-of-the-art chemistry laboratory and managing a research and development group that worked on nanotechnology using atomic force microscopes, near-field optical microscopy, and other techniques. Robert is also a co-holder of 4 patents related to nanotechnology. Mr. Powell is a founding board member of the Scientific Coalition for UAP Studies, or SCU. He was the director of research at MUFON from 2007 to 2017. He created MUFON's Science Review Board in 2012. Robert is one of 2 authors of the detailed radar witness report on the Stephenville lights, as well as the SCU report UAP 2013 Aguadilla, Puerto Rico. He is also the primary author on the recently published paper, A Forensic Analysis of Navy Carrier Strike Group 11's Encounter with an Anomalous Aerial Vehicle, and the secondary author of a paper published in the journal Entropy entitled Estimating Flight Characteristics of Anomalous Unidentified Aerial Vehicles. Robert is also a member of the Society for Scientific Exploration, the UFO Data Project, and the National Space Society. Robert is also a co-author of a book, major book in the UFO field, published in 2012, UFOs and Government, a Historical Inquiry, and is an author of a book designed for children, published in November 2020, entitled The Truth About UFOs, A Scientific Perspective. Robert currently resides in the now thought out Austin, Texas, restored power, fortunately, to Robert. Thank you so much. We are extremely honored by your presence, Robert, and so I give you the mic.
Thank you. Thank you, Mike, for that introduction. And let's see, I just want to, okay, sorry. Thank you for that introduction. And I want to give some kudos to Mick. He does an excellent job of getting rid of 90% plus of reports out there that are not real reports, or there's reasons where they're easily explainable. And line of sight is a very important tool in the study of UAP. But the key thing on line of sight is you have an infinite number of possibilities, right? Mick showed you one, which is the possibility of a balloon. You could have an object much closer, such as an insect that goes by at a slower speed, or a larger object farther out that goes by at a faster speed. So there are an infinite number of possibilities when the only data you have is line of sight. However, once you have an XYZ coordinate and know where the object is, then line of sight is no longer a critical aspect of the study of a given video. Now, let me share my frames. Okay, let me put this up. Okay, can you see that okay?
Perfect.
All right. Before I start, I do want to make 3 quick comments in regards to something Mick brought up, just in its part related to the UAP case on Aguadilla. The first, and this is something Mick could look at, is once using lines of sight, the object would have to turn to the north if it was a balloon in the last 30 seconds of that video. And that becomes problematic since the wind is east to the west. Second, whether the wind is 18 miles an hour or 8 miles an hour in his model, a basically lantern is a candle with a very lightweight envelope around it, and any significant wind collapses the side of it, and you can't move your lantern through the sky. And then third, Mick had some very impressive people who endorsed his candle theory. But one of them I'd like a correction, and that was the most credible of all, which is 3AF Sigma 2. That is an aeronautical group out of France. They did say that the lantern theory was possible, but what they went on to say was that it was not likely. And I have conversed with Luke Dean in person, so I know that is the case. So now let's go to the UAP report on Aguadilla. The first thing I'd like to just discuss is why do we even bother to look at a given UAP case? And why did we analyze this case? Most UAP reports, they're happenstance or anecdotal. It makes science very difficult. The analysis of UAP, when is it justified? Well, we only look at it if there's good quality data, there's quantity, there's multiple high quality observers, or there's a video or photo or radar or EN data. And the data is capable of providing some important information, such as shape, thermal signature, distance, XYZ location. We want, whenever possible, more than just line of sight. And most importantly, the object displays very unusual characteristics. We're not going to spend the time to scientifically analyze a quantity of data if it's basically to show us an object flying through the sky at the same speed as an aircraft, unless we can establish with that data that it is not an aircraft. And then once we've done that initial examination and we say, okay, here's something we can actually analyze, then a project is initiated, a report is done, and then SCU has a peer review team, which will review the report made by whatever individual or individuals. So I'm going to do two basic things here. I want to verify the video is real. I want to show you the video, show you the analysis of the video, and then our conclusions. Here's an overview of what happened. It was 9 o'clock, April 15th, over the airport. Homeland Security turboprop takes off. The pilot sees a pinkish red light coming from the northwest. Now, at this point, this already doesn't match the hypothesis of a lantern because the light's pinkish red, lanterns are reddish orange, and the light is coming from the northwest. It's not coming east to west over the airport at that point in time. The control tower sees the light. They receive no communication if that light had been an aircraft, and so they shut down the airport. The pilot engages a Westcam XM13 thermal imaging system, and he videos the object for 3 minutes. There's the aircraft that the pilot was flying, and you can see the MX-15 down near the bottom of the aircraft. This is important to know a little bit about this thermal system. This is not your average thermal infrared system you play with in your garage. This is a $250,000 system. It has an indium antimony detection system, which operates in a 3 to 5 micron range. And this is very important. These systems are capable of differentiating temperatures as low as 0.1 degrees Celsius. That's why when you look at this infrared video shortly, you can actually see the ocean waves. That's because it can actually tell the difference in the temperature as water moves up as compared to water sitting on the surface. This is the region, Puerto Rico. This little red dot, it was in northwestern Puerto Rico. That's where the airport is. And the first thing I want to do is tell you how we verified the video. Because we did not want to analyze this and find out that this was a fake video, right? So before you do hundreds of hours of work, you want to verify that the data is good. And this is a lot of the meta type data that Mick referred to. We use that same type of information. So here, I'm not going to go through this in detail, but all the information you need is on the video to give you the latitude, longitude of the plane, his altitude. So you know where the plane is all the time and you know when. So next, we get the radar data from the FAA. And with the radar data, we're able to match point by point the XYZ location of the plane and the time with what was in the video. So that's how we know this was a real video. Now, today, most of you know it's a real video, but when we did this analysis, we didn't. So we had to make sure this was real. Okay, now I'm going to show you the video real quick for any of you who have not seen it. All right, what you're looking at, I'm just going to pause it briefly. This is the object right here that the pilots were videoing. This is to the northwest. This is the ocean off the,
Robert,
the coast.
we're not seeing it.
Excuse me, Robert, just for a moment. I personally am not seeing the video. If anybody else is, they should speak up. Otherwise, the video has to be brought to the front.
Okay, what do I need? Oh, a new share, I guess.
Yeah, if the video is in a different app or a different frame, it needs to be
is.
shared.
Yeah. Okay. Okay, can you see it now?
Yeah, maybe go back to the beginning. It's great.
Okay, so here's the very beginning right here. The object, this is the northwest, the ocean northwest of Puerto Rico. Here's the object. You can see it if you follow my cursor. And this right here is the crosshairs in the very center. So wherever you're looking, that's where the crosshair is looking. That is a jet you just saw over the airport. And this is the object flying. I'll note, by the way, that as it's traveling over land, you can see the object occasionally dim, but you never see the object disappear. Not when you look at it frame by frame. So the object is black, which indicates hot. The white is cold, and the white you see around it, we believe, is an artifact of the thermal camera system. And as you can see, the object is rotating. Now, you notice throughout this entire time, you're basically looking at this one object. If this were, for example, a lantern, you would see the two lanterns with this system. You would not see this one heat zone. And I actually have a video of an individual who, using an inexpensive IR system, let go of two balloons, and you can easily separate them. So you know this system, $250,000, would separate them. Now it's going over marshy land. It's headed towards the ocean. I'm going to pause it just for a minute. You're looking at waves. That's the ocean in front of you. And the reason you see the waves is because of the high capabilities of this infrared system. Now the pilot has increased magnification. This is the ocean behind you. And there the object is where it goes. You can actually see it moving slightly under the water. I will go over the why behind that later. I'm going to stop this because I'll show you some other information shortly. And I'll go back to sharing my screen. Okay, so everyone can see my screen again?
Yes, we got it, Robert.
Okay, so there's two basic, I don't have time to go through this entire 160-page report, but there's two basic things I want to do. And that's one, establish to you that we know where the object was located. So we're not just dealing with line of sight, we're dealing with a known XYZ coordinate. And second, establish to you that this object really does split into two parts. Okay, the first I want to show you as to how we knew where the object was at is when it moves behind a telephone pole. Okay, if you follow my cursor, this is the object right here. This is a telephone pole, the lighter colored. The object's moving from your right to your left, and here's where it goes past the pole. If you look at this magnified view below, you can see the object's heat signature. And if you notice, it's vertically cut off because the pole is vertical right there. This is an indication that we know exactly where the object was. Second indication, the object goes behind a tree. We know the exact geolocation of the tree, so we know the XYZ coordinates of the object. Here's the object. You can see the dark area. These are frame by frames. You can see it starting to dim. It dims further. And then in the last frame, the object is completely gone. There is no indication of an object. Okay, the next piece of evidence we have is we have 6 pieces of evidence that tell us we know the object impacted the water. And I will show you how we know that. So I'll go to the and stop share. And okay, just want to, can you see my the video on the screen at the moment?
No.
Okay. Let's see. Can you see it now?
No.
Okay. All right.
Is the new video you want to show in the same app as the other one?
Okay, I've got it now, I believe. I think you can see it now.
Yes, great.
Okay, so I'm going to back it up a little bit. This is a far off distance view of the object. You can see it. It's right in the middle of the crosshairs. As I move the frame forward, you will see it touch the water, and you will see a darkened area where it impacts the water. Right there. If I'm just going back and forth over the area where it's touching the water, and I'll let you see it in real time. Right back there. So that's a video of the object impacting the water. Okay. And I'll share my screen again. Sorry for this delay. All right, so that's one reason we know it impacted the water. Second reason is based on a sudden loss of the signal. It's not gradual. So this is a close-up video of the object, 1/30th of a second prior to water impact. So you can see it consists of about 60 different pixels. Now, this is 1/10 of a second after water impact. 3/10 of a second after water impact. So the argument that sometimes is made is that the camera just lost the object. It just happened to disappear on the camera. But this is not what you see when a camera loses its focus. You would still see part of the object. And this happens within 1/10 of a second to 3/10 of a second. The next item is when the object, the signal loss is gone, the object's gone 5 to 10 seconds. And I'm not going to, because of the problem I'm having on the screen, I'm not going to show you this video at the moment. But basically, if you look at the main video, you'll see the object go into the water for about 5 seconds, then come out of the water. And then at another time, it's in the water for about 5 seconds. So this isn't like a gradual dimming of an object. And here is the next reason we know the object entered the water. If you look on this graph, on your x-axis, these are frames. So this is basically time going from left to right, and speed on your y-axis going from 0 to 120. At the point in time the object enters the water, it's moving at 115 miles an hour. As it enters the water, the speed does begin to slow. It doesn't slow like you would normally expect an object entering the water at 115 miles an hour, which would be a sudden stop, but it does slow. So we know that this isn't just a balloon traveling through the air that coincidentally happened to slow at the same time that visually to our eyes, we see the object disappear. We know that these match up. Okay, the next thing I want to spend the rest of my time on, because let's see, it's running short on time, is the actual parting of the object.
Robert,
What you're looking at here is frame. I'm sorry.
You can take a little extra time, Robert. We went over, so don't worry.
Okay, so the what I want to establish to you here was when the object actually splits, because this is the most interesting part of the entire video, in my opinion. What you're looking at is a graph. On the x-axis, you're looking at frame count. So this is going from left to right. So this is basically time moving forward, left to right. And this is the number of pixels making up the object that's on your y-axis. So where you see the word normal variation, you have a certain amount of variation in the camera system. And also in how we define, okay, is that a pixel or is that the ocean background, right? So the object's in the right here. This is normal. This is where it's been. Now there's a gap because that white crosshair, that reticle, interferes with counting at certain points in time. And then here's as you go forward in time, here again are the pixels making up the object. Now, we go through about 10 frames and the number of pixels begin to increase. And that's at about on about 44 frames. Now at 52 frames, 8 frames later, which is 8/30ths of a second, the object's continuing to increase, and it's a fairly good linear increase until you get right up to here, where you have 70 pixels making up the object. That is roughly double the size the object was. At that point in time, the object splits, and you now have 2 objects of equal size. So we haven't lost, we've gained mass going through here, but we haven't lost any once it splits. We now have 2 objects. Okay, now this is so important. I want to show you a detailed frame by frame. So let me explain a little bit what you're looking at. Okay, where do you see my cursor circling here on the left? These are the amount of heat each pixel is displaying. So on this camera system, you can have a value from 0 to 256. And 0 would be your maximum heat that the camera indicates. 256 would be your coldest point. So all of this white area is ocean, and these values are between 120 and 140. So this is the colder region. Now this color I have arbitrarily colored to make it easier for you to see. So the yellow is in the 70 to 90 range on this particular frame. And then you have it gets warmer in the center. And then you have an extremely hot point right here. And here, okay, so that's in frame 4563. This is a normal image. This is kind of typical of what you see during its movement. Now, this one is also a normal, but I just want you to see how it can vary a little bit, right? Both of these are normal images. Okay, now we're going to move forward as the object begins to increase in size. So here's frame 4611. Let me go back. That was frame 4590, right? 4611, that's 20 frames later. So this is 2/3 of a second later. We now have 49 pixels. And here's frame 4623, 41 pixels. And notice also how the heat zone is increasing. Let me go back. See how the hottest heat zone was a much smaller area? Now this hotter heat zone has gotten much larger. Now let's go forward a little more in time. Here's that hot heat zone again. It's gotten much larger. The object overall is continuing to increase in size. We're at 58 pixels. Now go forward 3 frames, 4641 to 4634. That's 1/10 of a second. Our pixel size is still about the same. However, we now have a bimodal heat signature. We've got a very hot area here and a very hot area up towards the top. So it almost looks like it's beginning to separate. You go forward a few more frames and it does begin to separate. You still have one object, consisting of 61 pixels, but there are now 2 heat zones within that object. And now you go forward 12 more frames, which is 1/3 of a second, and the object is actually split apart, and we now have 2 objects. So what you're looking at almost reminds me of mitosis in biology. It's pretty crazy. So I'm going to show you a video now, clip of the object splitting. Let's see, where is that? Okay, I've got it.
We see it.
Okay. So this is actually the object entering the water and is not the one that I want. Okay, I've got the one that I want. If I can just. geez. Hold on just a second. Okay, I'll tell you what I'm gonna do. I'm just going to explain what happens because I'm disappointed with myself on this. Okay, so what if you go back, you'll be able to see, but what you'll see is the following. You will see the object slowly splitting apart on the screen. And as you see it splitting, you will notice that the objects, there will be two objects and they'll be moving apart, right? So one of the arguments is that perhaps what we're looking at is a reflection, right? That this is not really an object splitting, but an object reflection. Well, there's several reasons that would not be the case. One is the waves that day were 6-inch waves. So you've got 6-inch waves and you're trying to develop a reflection, plus water is an excellent blocker of infrared. So you're still trying to, come up with a reason how you can have a reflection. And then as you look at the video, right, you have the two objects. The first object you will see is as it appears, you'll see it disappear into the water and you have one. And then it comes back up. And then the second object disappears, right? So now you've got a problem because you have your primary object that you thought was causing a reflection, and now you have it disappear. And at the other time you have the reflection disappear, right? So you can't, what should be disappearing is the reflection, not the primary object. And we see both disappear. The other thing that happens is during that time that it splits, you actually see the objects move farther apart. So they're moving away from each other. So I think the idea that this splitting is a reflection is very difficult to buy into that as a possibility. Okay, so to summarize, on the balloon, that is eliminated due to wind direction, speed, size, object's thermal signature, concept of a bird, also speed, size, tumbling movement. The drone was what we thought was the best opportunity at an explanation. Although it would indicate you have a government agency willing to fly a drone near a commercial airport through a residential area at night without a light. But the speed through the air, right? A drone could explain the speed through the air. It could explain the object size. It could explain the movement, and the heat signature could be explained by a battery-powered operated drone. Now, the minimal water impact is a little more difficult to explain, but I wouldn't say that, okay, it can't theoretically be done, that someone has developed a drone that can impact the water at high speed with little water movement. That's possible. But the two artifacts that are harder to explain with the drone hypothesis is that, one, you've got an object that once it went into the water, remember it was at 110 miles an hour, it slowed down in the water, and at the point it left the water, the speed had dropped to 40 miles an hour. But it is still moving from water to air at a speed of 40 miles an hour. Okay, normally, most drones are going to either float to the surface, then go into the air. There's some drones that can do that. Or if you have, for example, like an ICBM on a submarine, he can break that water plane, but he's got a rocket engine propelling him through. There's no indication here that there was a heat source pushing the object out of the water. So that's difficult to explain. But the most difficult to explain is the splitting into roughly 2 equal parts. That is what I find to be the most unusual part of this entire video, is how this splitting occurs. The other thing I wanted to say is our paper has been reviewed by 3AF Sigma 2. That is a French aeronautical group, and they were very happy with the paper. GPAN of France in October also commented on the paper. They felt that there was no satisfactory explanation for the video. So in conclusion on this, all we can say for certain is that we can fit no known aircraft, no known bird, animal, or anything else that explains what we see in the video. You can get additional information, the entire 162-page report at our site here. Now let me stop my sharing. All right, so I can take questions.
Thank you, Robert. That's really, really fantastic. And so thank you, Mick West and Robert Powell. This is exactly the kind of thing that I would like to see much more often in the community, is looking at a very detailed case study and diving very, very deeply into the details there, a close reading, as it were. This is great. So I thank you again, Robert. Absolutely excellent. Now we have somewhat of a dilemma because we are about 3 minutes before we were supposed to end. So I will borrow some time from our break. So I want to give Robert the full 15 minutes for his questions. With that in mind, obviously, if anybody does need to depart, it's fine at 12:15, but I'm going to extend this by 15 minutes. So I will turn it over to our discussant, Massimo Teodorani. Dr. Teodorani, please take over.
We can't hear you.
Yeah, Massimo, you seem not to have, although you're unmuted, we cannot hear you. I think he's unmuted, right? Yeah. No, we can't hear you. Still cannot hear you. No.
Maybe try plugging and unplugging your headset.
Yeah. No, still nothing.
Now?
Yes.
There you go.
Oh, you say, sorry, today it's full of problems. First the internet, now this one. Okay, congratulations for your very interesting presentation and for the results that you are obtaining with the publication of this work. I collected and selected some questions, and I have one of mine. My one is, how was the speed measured? I see that there is a variation. It's oscillating between 100 miles per hour up to 70 miles per hour. At least it reminds to me with time. How did you measure the speed?
So the way we measured the speed is once we knew a location. And okay. So we're looking at the object as it's moving across the path. So then at that point, we're looking at time and the distance it moved in a given time.
Okay, perfect. And I have selected some questions in particularly 4 questions. One is from AP Simmons, who asked, was a splash observed when it appeared to go under the sea?
Massimo, can I intervene? I'm sorry. Can we allow Mick West to respond given that?
Oh, sorry, Mick. Yes, I didn't see his hands. Yes, Mick, go ahead.
Thank you very much. Real quick, I'd like to apologize to Robert for my misrepresentation of the 3AF report. I meant to say that they didn't eliminate the lantern hypothesis, and I got my slides mixed up with the Bixby slide. But my question here is, why is Appendix L still in your report if it's been shown that it's in error? Like you say in Appendix L right at the start, the entire thing is based upon these 2 frames of the video. And you see that the background does not move between the 2 frames, but the object does. And the person who wrote that appendix assumes that that means that all of the motion comes from the motion of the object. But of course, the plane is still moving, so we're still getting a contribution of parallax. So the calculation in that appendix is entirely wrong. So the fact that this has been pointed out to you several times over the years, and this is still in the report, I just checked on the website just now, makes me and probably other people less likely to delve into the other aspects like the thermal stuff that you mentioned, which I think is very interesting. So I just want to know why you're leaving in things that have been shown to be wrong.
Right. Well, I believe there is it's reasonable that there may be an error in Appendix L. Sometimes, especially a 162-page report written by 5 people, you may find an error somewhere, right?
But it's the entire thing, because the entire appendix is based upon this one calculation at the start of the appendix.
Okay. The
distance.
The distance does not depend on Appendix L. Appendix L depends on itself. But there are
the distance
other
that is used in
areas
Appendix L is
Pardon?
the one that is wrong. Appendix L starts out with a calculation of distance. That
Right.
calculation is wrong. Then Appendix L goes on to build an entire analysis on that one number, which I think is like 1,600
Right.
feet or something.
What I'm saying, Mick, is
1,200 feet.
Appendix L, you can throw Appendix L out of the report, and it does not dissuade or change the results of the report.
Okay, I would just recommend you do that, because otherwise it makes it difficult to take the rest of the report seriously, and that's all my point. Thank you.
When I can get it on my list of 100 things, I will get on that one.
Okay.
Other questions? I think,
yes.
Massimo, you have one.
I have no. I would say no. My one was only about the speed, but I collected.
Yeah.
But I just collected some others since the beginning of after the end of your talk. One is from Mark Elowitz, who is asking, why are the video frames so choppy? Is this due to a very low frame rate of the infrared video, or is this simply the result of a low bandwidth on the internet playback?
Oh, well, I'm not sure what they mean by the choppiness of the video.
I have no idea,
because I broke them out frame by frame.
Yeah.
So I guess I'm not sure how to answer that question, because I'm not sure what the question is.
Yeah. Well, I'm just reading what I copied and pasted from the chat. There is another question from AP Simmons, who is asking, were there any other objects radiating heat that were captured in the video that we can do a heat comparison?
Yes, there were. We actually had that in the report. You can see cows in the video, and we do a analysis of the possible heat of the object. The problem is, we were able to determine that the object's heat was at a minimum of 105 degrees because that was the temperature of the cows. But what we don't know is the object, the camera, has 259 different values it can apply across the temperature band. We don't know if that's done in a linear fashion, a logarithmic fashion, or like in a Poisson equation type fashion. So we can't determine the object's exact temperature. The only thing we were able to determine is a minimum temperature.
Okay, there is a very recent question.
We actually we have a hand up. Rich Hoffman has his hand up. We should take the
Oh,
live
sorry,
questions when we can.
I didn't see it.
Okay.
Okay, so go ahead, Mitch, Rich Hoffman.
Yeah, I was going to just mention that I was just going to mention that some of the things in terms of the choppiness and the playback appears to be like internet. We also used we had slow show the breaking apart of the objects, that type of thing. The other thing I'll point out to you is that the object did have a light on it when it was first coming in from the water. There was description of it being a pinkish red, and that the light did go out. And that's what triggered them to turn on the thermal camera and beginning making the actual 3-minute and 54-second film. Just wanted to bring that up. That's all.
Okay, thanks, Rich. And Massimo, I see there's another person with a hand up, Richard O'Connor, I believe.
Yeah, I'll give him that.
Yes, go ahead. Richard, go ahead.
Richard, you can open your mic and camera now.
Okay, yeah, I just wanted to kind of state the obvious here that if this was a Chinese lantern, when it submerged, the candle would have been extinguished, and it wasn't. So that seems like kind of a self-evident bit of information that sort of extinguishes the Chinese lantern hypothesis.
Okay, so yeah, I think what they're arguing with the Chinese lantern is they're arguing that, at least these are the arguments I've heard, was that it did not really extinguish, it just disappeared for a while, that the camera failed in its resolution capabilities, and then it reappears, the camera's resolution fails again, and so that appearance and disappearance is an issue with the camera. So this is kind of something that we've talked about before, where you string along a lot of arguments. Well, maybe this happened, and you start multiplying together the likelihood of all of these possibilities happening together, and it becomes very small likelihood.
Yeah, especially for a $750,000 or a $250,000 camera.
Right.
Thank you.
Yeah, I don't see any other hands raised. Maybe if there is time, there are other questions that I recorded.
I do have a video that I think I can do this one quickly and share with you. And this is a video taken of two balloons tied together to try to see what would that look like in the infrared. So I'll share my screen.
Okay.
And okay, can you see that?
Yes.
Okay, so what you're seeing, and this is not even a lantern. These are just actual two balloons tied together. And this was done by Chris Ebert. And he, as you can see, I'm just moving it along. You can see, and I'll just start it up. Here's the balloon he's looking at with an inexpensive infrared camera, nothing like what the military used in that. And you can see the two objects. Where'd they go? Let me go back to where they were at. Here they are here. And you'll see how there's two right there. You can see them moving apart and together. it's very easy to separate them. And in the case of the Aguadilla video, you don't have an inexpensive infrared camera like this one. You've got a $250,000 camera and 3 minutes of video, and we're not seeing any indication of two objects.
So if I can intervene there, Robert, so then what therefore would be the explanation for the appearance of a spheroid and no evidence of individuation on the lantern hypothesis? I don't understand that. And secondly, what theory or hypothesis can explain all of the data? So Robert, you know, no one's really focusing on the other bit of data, which is radar evidence. Is that correct? Was there not a radar track?
Let me start with your second question. Yes, there was a radar track. The radar is to the northwest of the island, which is the direction that the control tower and the pilots indicated they saw the object. And I just did not have time in this presentation to cover everything. But the radar tracks are seen prior to the aircraft leaving the airport and seeing the object with their video system. And then at the time, so let me backtrack. So you have this object moving across towards the island, then it disappears off radar. And then you have the aircraft leave, and the aircraft begins to see the object with visually and then with infrared. So what we can't explain is, okay, so why can't we see the object on radar now, right? So there's two possibilities. Either it's disappeared off radar, or number two, the object has dropped low enough that it's no longer on radar. The radar site's 50 miles to the east, and using the plane, we were able to intrinsically determine that once an object drops below 400 feet, it will disappear from radar. So one possible scenario is you have an object approaching the island, it's dropping in altitude. At the time the pilots see it, it's dropped below 400 feet, and that's why it's no longer on radar.
And Daniel Kuhn calculated, by the way, two velocities for this object being tracked, correct? One was Mach 1.2 and the other was Mach 2.1. How do we explain that?
I'm not, I haven't seen, his calculations, so I don't know. Oh, okay. He's talking about the radar data.
Yes.
Okay. Yeah. Well, yeah. Let me comment on that. When I looked at the radar data, you basically have the target is moving in a general area towards the island, but it's just jumping back and forth. And if you calculate, if you do a calculation, yes, you will get a Mach 1 or Mach 2 speed. And I just found that is very difficult to explain. When I sent it to the Sigma 2 3AF group in France, and they analyzed the report, they actually had a very good explanation that made sense to me. And what the French guys said was that this is very similar to what happens when you are scrambling a radar system, especially with, or if you had a plasma. So basically it's like your radar beam is hitting that target, but it's not coming back at the proper time exactly. So the location of your target is jumping around, not in reality. The target's not really jumping around, but the radar response is being caused to jump around because it's being jammed. And I had not considered that possibility till the French pointed it out. Now, here's the two questions. Was it jammed intentionally or unintentionally? My gut feel is that it's unintentional, that the object may have a plasma around it, and it's the plasma that's causing what we would perceive as jamming, but not necessarily intentional.
This is another anomalous observation that must be accounted for, therefore.
Right. Yeah, it's just, in 30 minutes, it's hard to cover 162 pages.
No, I know.
But I'm glad you brought that up.
Yeah, I mean, we have to account for all of the data, right? There are observations, thermal data, radar data, eyewitness accounts. This is right. We as scientists, and philosophers and thinkers, we have to account for everything, right? We can't just focus on a single aspect. So this is very, very fascinating. I wish we had much more time. This is just super, super interesting. Hopefully Mick West will follow up in the comments and perhaps be available in the general chat room to continue this discussion. It's super fascinating. Again, this is the perspective Limina and the society has taken. This is an open discourse. This is in the interest of the free, you know, the sort of the free pursuit of knowledge and an inquiry here. We want all the facts, all of the data on the table, rational discussion and analysis of every aspect that we have observed for all of these interesting cases. Thank you so much. Thank you, Massimo. Thank you, Robert. And thank you again, of course, we're very honored to have Mick West with us.